Okay, so it is a pleasure for me to welcome Hector Geffner. Hector is a senior researcher affiliated with the ICREA and the University Pompeu Fabra in Barcelona. There are very many things I could say about Hector, but let me say one or two. So he got a PhD in 1990 from UCLA under the supervision of Judea Pearl, and he got an the ACM Dissertation Award for that. And since then, he's been working in AI in various places, and his research spans many sub-areas of AI, such as uncertainty in AI, knowledge representation, planning, search, and some machine learning. So he was the ideal person to give a talk on the evolution of the contours of AI, which is this year's special theme. Hector, you can start.
Okay, so thanks, Jerome. Okay, thanks, Jerome, for the invitation, the organizers for the invitation as well. And yeah, so the goal of the talk basically is to play some recent advances, especially in machine learning in a broader context, okay? I'm gonna tell story in the old-fashioned way, meaning I'm not gonna have videos, very few pictures, okay, and some bullet points to try to make the points of this story. The story, okay, as models basically do not have to be fully accurate, okay, they are also subjective, so some of these are of course my views. So the question and the challenge is whether to make it coherent and hopefully insightful. So let's see. More or less, the story will go, we'll start with the AI programming. Okay, some of you probably are too young even to have heard about AI programming, but I talk a little bit about that because I was dominating paradigm for a number of years in AI, then the problem of generality. So we'll talk about learners and contrast them with solvers, okay, and eventually we'll try to draw some parallels between learners and solvers, and both learners and solvers on the one hand, and some current theories of the human mind that postulate, okay, a couple of processes known as System 1 and System 2, okay, that will also provide some map about some of the challenges. Okay, so this is more or less what I want to do. I'm not going to be displaying references, not even self-references in my slides. If interested in the references, please look at this paper. In the proceedings, 2 pages of the reference, you will find everything, okay, that is related, or not everything, but a lot of work is related to what I'm going to be talking about, okay? And at parts, I'm going to be talking about work done in our group, and of course, this is work done in collaboration with a number of students, colleagues, and friends, some of whom I'm listing right here. So let me start. I'm not going to start in the Dartmouth meeting, okay, that's going too early, but this actually is a pretty early book on AI. It's a collection of papers, very influential, published in 1963. Probably one of the first AI books, and actually the first that fell into my hands when I was an undergrad student in the early 80s. This is basically a collection of contributions describing programs, okay, for playing chess, checkers, okay, proving theorems and things of that sort. Okay, the notion of working computer programs is very important, was very important even in the selection of the contributions, okay, that appear in this seminal book. Actually, in the 63 edition, the original edition of the book, okay, the editors said, we have tried to focus on papers that report results. In this collection, the papers describe actual working programs. Because of limited space, we chose not to avoid more speculative pieces. And actually, this point is restated in the more recent 95 edition, where they say that the critical selection criteria was that the paper had to describe a running computer program. All else was talk philosophy, not science, and little has come out of the talk. Okay, so if a computer scientist calls you a philosopher, don't take it as a compliment, okay, normally. So one actually can argue that some of the main contributions, okay, done in AI in the early decades, in the 60s, 70s, and earlys, had a lot to do with programming and the representation of knowledge in programs. Okay, from this time we get Lisp and its influence, what was a functional programming, Prolog and logic programming, rule-based programming, and many, many other ideas. Actually, as Jerome mentioned before, I did my dissertation in the late 80s, and at that time it was not unusual to do a dissertation by picking some topic or some domain, you analyze and so on, and you try to capture the reasoning of an expert or yourself when trying to address this domain X. That could be anything, okay? Understanding jokes, understanding stories, drawing analogies, and things like that. Actually, many good ideas came from this work, okay? The whole idea of AI programming and so on, but there was a methodological problem. And the problem was that these programs, okay, behave in a reasonable way over the examples and the scenarios anticipated by the programmer, but were not sufficiently robust or general outside of these examples. So if we look back, okay, and simplifying things a bit, one can say that beginning in the 80s, okay, that there has been some sort of methodological shift in AI research, basically from writing programs for ill-defined problems to designing algorithms, okay, for perfectly well-defined mathematical tasks. Okay, and the learners and solvers that I'm going to talk about actually have this crisp functionality. They both can be understood as mapping inputs into outputs, okay? And these algorithms, the algorithms that underlie learners or solvers, are general because they're not tied to particular examples, okay? So rather they are tied to general mathematical models, or models expressed in mathematical form and general tasks. So what I'll do now, I'll try to devote some time, okay, to get into some detail, okay, not too much about learners or solvers in order to draw some comparisons, okay, between them. Okay, by learners, I'm going to be referring mainly to deep learners and deep reinforcement learners that are the ones behind, okay, all the excitement and all the great news, okay, from AI in the last few years. Both deep learners and deep reinforcement learners can be understood as computing functions, okay, whose structure is encoded in a neural network and some adjustable parameters, okay? So in a deep learner, the inputs may represent images and the outputs may represent labels, or the outputs may represent bounding boxes. In deep reinforcement learning, so the inputs may represent the state of a game, and the output may represent the value of that state, the action to be done in that state, and even the probability distribution, okay, of the actions that can be done in this state. In all these cases, okay, the parameters of these functions are tuned by a training process where you're trying to minimize some error function. The error function, okay, is different in the case of supervised learning, okay, in deep learning, and in deep reinforcement learning. In one case, basically you're using a training set. In the other case, you're trying to get the values of states to be consistent with the values of successor states. The details for this do not matter much. It's sufficient basically to say that building on ideas from the 80s and 90s with more CPU power, more data, deeper nets, attractive problems, and so forth. Okay, so this method have delivered true breakthroughs in a number of tasks, okay, tasks such as image understanding, speech recognition, and even superhuman performance in very challenging games, and even games that were completely out of reach, okay, like Go, chess, and so on, and in certain cases from self-playing alone, okay? This is a major achievement, and it's clearly one of the most important milestones, I would say, in the history of AI. Sometimes you hear that, okay, it took a lot of training and so on, but even the training took, rather than weeks, okay, took months or a year, this will still, okay, just learn how to play Go at the world level or chess, okay, will still be main milestones in the whole history of the field. This, of course, does not mean that human-level AI is around the corner. Okay, and there are many things that one cannot do with these methods, at least right now. So, in some sense, it's ironical that we can use these methods to play chess or play Go, but we cannot use these methods to solve our beloved blocks world. Okay, and one of the reasons for this is because these methods presumes that the inputs have a fixed size. Okay, while I'm aware of convolutional networks, recurrent neural nets, that you can deal with images sometimes of unbounded size, sequences of unbounded size, okay, this does not mean that you can deal with structures, arbitrary structures of any size. In any case, I'm going to come back to this point later on, okay? On the other hand, we have the second type of programs that I mentioned, okay, solvers that also map inputs into outputs. So we have solvers like SAT solvers, classical planners, Bayesian networks, okay, CSPs, okay, and so on. Basically, these are models with their solvers, and in this case, the output that you want, okay, from these solvers, you don't learn it from training, but basically it's implicit in the model. So what the solver has to do, in some sense, is to make this answer explicit for the given input. So in a SAT solver, so the input may be a formula in CNF, and the output will say, okay, whether the formula is satisfiable or not. In a classical planner, so the input will be a planning problem, and the output will be a classical plan, and so on. Again, these type of models, these type of solvers, they are general, they are not tied to particular type of examples. Okay, some of them are extremely expressive. Okay, I mentioned in particular POMDPs that are almost AI complete. Okay, and in this case, so one key difference, okay, with learners is that, of course, the size of the inputs is not bounded. Actually, it's the source of the complexity. Okay, the complexity grows with the size of the inputs. Not only that, in all of these models, basically any complete algorithm is going to be run in exponential time or worse. So the challenge for solvers is not to break on an input, not to break on a problem, just because the problem has too many variables, and the methodology is basically empirical, benchmarks, competitions, and so on. So let's take a first look at this contrast between learners and solvers. Okay, while they both map input into outputs, they do in a very different way. In learners, you require experience of related problems, okay, in order to compute the function f. Then all you have to do is to apply these functions to new inputs. On the other hand, solvers work out of the box without training, but on each given input, they need to think a bit. Okay? In the worst case, more than a bit. Actually, I would say that thinking is these days probably has a bad reputation, okay? But it's not something that is bad, okay? Thinking is hard, but computational limits are always a good source of insight. So many of you like Bayesian networks. I do. Bayesian networks are used by cognitive scientists to understand how babies learn, for instance. And the fact is that Bayesian networks were invented as a way to tame the complexity of reasoning with probabilities. So what I'm going to do now is to look at some powerful computation ideas in the area of planners. Planners are solvers, okay, just focus on behavior, okay, in the generation of goal-oriented behavior. So let's take a look at the first problem. It is a most basic problem in planning. The problem here is to find plans, in this case deterministic plans, and basically this problem amounts to finding a path in a graph. The difficulty is that the size of the graphs is exponential in the number of variables. So how planners or some planners manage, okay, with these sorts of complexity, okay, in some sense they appeal to a relatively old idea, okay, that appears in the works of a number of people, okay, and the whole idea is if you do not know how to solve a problem P, solve a simpler problem P prime and use the solution of P prime for solving the original problem, okay? In the case of planning, this idea of problem simplification or relaxation, as it is normally called, okay, so the main transformation is what's called the monotonic relaxation, also known as the delete-free relaxation. And in that case, all you have to do is to take a compact representation of the planning problem, and you relax it by making the effects of the actions to be monotonic in the variables. What this means is that an action changes the value of a variable from one value to another. In the relaxation, the variable has these two values. So the old value is not lost, okay? You get a new value. The relaxation doesn't make any sense physically, but it makes perfect sense logically and in particular computationally, because this relaxation makes the problem decomposable, and by making the problem decomposable, it makes the problem tractable. So now you can go to P prime, okay, to the monotonic relaxation, solve that problem, and use the length of the solution, of the cost of that solution, as the heuristic value of the original problem. In contrast with learners, so this is method that is domain independent, okay? It doesn't depend on the nature of the problem. You do not need experience on related problems in order to use these methods, okay? You just get this method, and in this sense, you get a sense of direction in the search of plans for any plans. Let me move to another example, okay, about things that you can do with a planner that in some sense illustrate the contrast, okay, between solvers and learners. Actually, a good problem, okay, to illustrate this contrast and these commonalities as well is goal recognition. Okay, and the reason is that goal recognition is a classification problem, okay? And basic classification problems look like learning problems, okay? But they can be tackled sometimes in another way. So let's look at the picture over there. So there is an agent that is moving away from S, okay? So you observe that the agent is moving up, it's doing 2 steps up. And you know that the possible goals, the possible targets of this agent are one of the letters that are shown. So if I ask you, what is the goal of the observed agent? Is it B? Is it A? Is one of the bottom? And so on. What do we do? Okay, it turns out that the solution to this goal recognition problem, okay, can be cast in a way that you can solve it by using Bayes' rule, okay? Okay, you are looking for the posterior distribution of the goal given the observation of the behavior of the agent. And on top of Bayes' rule, you need, okay, cost considerations. Why, when you look at this problem, it's more likely that it's going to B rather than to F, and to H, and so on? Because it doesn't make sense. If the agent is really trying to get to H, okay, it should be moving down, okay, not up. Okay, by moving up, it's increasing in some sense the cost of getting to one of the goals in the bottom row. So at the end, you can take these cost measures that can be computed by a planner, and from these cost measures, okay, uses to get the likelihood function, and Bayes rules to get the posterior distribution of all the goals. And once again, this is a classification problem, but we are solving problems from scratch, okay? So it doesn't matter what the problem is about, okay? This is a domain-independent method that can be used to any problem with no training, okay? Again, so trying to reemphasize this point about the difference, and this is a classification problem where we are trying to map observed behaviors into a finite set of possible goals. Okay, so a third illustration, okay, that again shows the contrast between learners and solvers arises in the sub-area of planning that is called generalized planning. In generalized planning, you're interested in solving not just one instance, but in getting a strategy that will work over many instances, okay? In this case, okay, the task is to move the eye, that is this circle that we see in the bottom left, okay? So the scene is like a block's world scene. There are many blocks there, and the agent can observe the contents of the cell that contains the eye. Okay, so in this case, it can observe that where the eye is located, there is no block. If it moves the eye to the right, it's going to find that there is a block, but this block is not green, and so on. The figure on the right, what it shows is a two-state controller that solves the problem here. Okay, basically, the problem is about moving the eye to a block that is green. And what the controller actually is doing is moving the eye from left to right. Whenever there is a block, it moves the eye all the way down, up, and then all the way down, and then keeps moving right. And in this way, it's scanning, okay, for all the set of blocks that you have. The interesting thing is that the planner, actually classical planner for deterministic actions, okay, has obtained a controller that is shown on the right. So the controller on the right, okay, that involves partial observability and feedback and so on, has been obtained with a classical planner after some transformations. One thing that is also interesting about this method, in particular in contrast with learning, is that the controller that you get by running a classical planner only once on a single instance, okay, will not always only solve, okay, the instance that we have on the left. It will solve any instance of the problem, okay? Change the location of the blocks, change the number of blocks. The controller that you got by running a planner only once will work in all these cases. So this is a case, basically, where the output, in this case of the solver, is not just the function of the input f of x, but it's actually the function itself, because now this function can take other inputs, and this function is already computed, and this function has been computed by running the planner only once. Okay? Last illustration about what planners can do before we go back to the contrast between planners and solver. Okay? It's about some pretty successful polynomial algorithms that have been applied to problems, okay, that generate exponential spaces. Okay, the simplest algorithm of this kind is what is called IW1, and IW1 is a very, very simple algorithm. Okay, it's like a breadth first search. Okay, you start doing a breadth first search, but it works with a set of features. So the set of features, Boolean features f, is given. And IW1, what it does the breadth first search, and when there is a state generated in the search that does not make a feature true for the first time, it prunes the state. So basically, IW1 prunes most of the states and leaves unpruned or expanded basically a number of states that is linear in the set of features rather than being exponential, as will be the case of plain breadth first search. IWK is IW1, but with a feature set, okay, that is basically made out of the conjunctions of up to k features from F. Okay. Two remarkable things are there are many, so if you take benchmarks, okay, that people have considered in planning and so on, so for most of these benchmarks can be solved with IWK for a very small value of k, even if the problems, okay, as I mentioned, involve exponential spaces, okay? Actually, not only you solve this problem, okay, but you can prove that you solve them optimally. And again, this is a theoretical result for these domains. Okay, I say, okay, blocks were problem, logistics, whatever problem, okay, one can prove these results. It's not something that we get out of the instance. You can show that this algorithm will show many of these instances, especially when the goals feature single atoms, okay, in polynomial time, even the size of the space is exponential. Okay, actually, just mention a couple of variants that I think that are relevant, and one of them actually will tie well with the work in learning. There are some variants of these ideas that are, for instance, one of them, okay, BFWSR, is a state-of-the-art planning algorithm that builds on this idea, and it's actually the first planning algorithm, I would say, from the 50s, okay, start with GPS, that can compete with the planners, in particular with PDDL planners on PDDL benchmarks without using action structure. So in a way, now we have one type of algorithm, okay, for classical planning problems that actually has the performance of a state-of-the-art algorithm. And for the first time, it doesn't work with the structure of the actions. It only uses the structure of the state. So you know the atoms that are true in a state, but you do not need to know what are the action preconditions, what are the effects, and so on. Okay, so basically, this by itself almost solves the problem of the syntax. Okay, it doesn't matter how you express the action, the language that you have. All what we care is what the actions do in the world. So the semantics, the state transformation, and the set of actions that are applicable in a state. So this, again, is a variant of exploiting, okay, this finding that I mentioned above. So a second, okay, result I got of this is that we use a variation of this idea, what's called rollout IW, so a version of the IW1 algorithm, okay, as an online planner to play the Atari games directly from the screen. So in a way that we get similar inputs from the ones using reinforcement learning. Actually, it turns out that this online planner does pretty well, comparably well, okay, with the more famous, okay, deep reinforcement learning, DQN, okay, using basically the same information, working directly with information from the screen pixels. Now, these basically are using two different approaches for the same task, but when you look at these two different approaches, they sort of illustrate the contrast between learners and solvers that have been mentioning so far. So DQN, okay, so DeepMind's algorithm and architecture requires lots of training data and time, and then plays very fast because they computed the function, and all they have to do is to apply the function. On the other hand, the planner rollout IW1, okay, so plays out of the box without training, but again, has to think a bit before each move. In the case, it's almost, okay, real time. In the case that resulted, okay, half a second per each move. But this illustrates very well the general point, and one sort of possible take-home lesson, okay, from the talk today is about this concept. So let me re-emphasize this point again. So learners do require experience on related problems, but then are very fast because they compute these functions that they can then just apply. Solvers can deal with completely new problems from scratch, but they have to think a bit for each input because they're not computing these functions themselves, okay? So this is the first take-home message. So let me go with the second general take-home message, that is that there is a strong parallelism, okay, between learners and solvers on the one hand, and these dual process accounts of the human mind that were pioneered and also popularized by Daniel Kahneman in his book Thinking Fast and Slow, okay, where basically the mind is postulated by operating like in two modes, okay, that are combined, they are not independent. On the one hand, we have a system one that represents the intuitive mind, what comes easily to us, okay, that is fast, associative, and conscious, doesn't require any attention, is effortless, parallel, specialized, and so on. On the other hand, okay, there is what's called system 2, okay, or system 2 process that correspond to what we could call the analytical mind, and is normally, okay, associated with the slow process that are deliberative, okay, are conscious, effortful, serial, general, and so on. By the way, by putting learners, I don't mean actually learners, by the result of the learning. So the black boxes that are produced by learners is what I'm trying to fit in the first column. So I tend to think that this is a good illustration about, okay, so what is the scope and capabilities of learners and solvers. By the way, so if you take task, let's say learning to drive, so initially when you learn to drive, okay, you have to pay a lot of attention, and it's basically a system 2 activity, okay, with many system 1 activities involved as well. but you become more familiar and you drive more, so most of these activities become automatic, and driving becomes, for the most part, a system one activity. In the exception, when you're trying to pass a car in a freeway and another car comes in your way, again, then, you stop talking, and you focus and go back to your system two to figure out what to do. Same thing in other activities. For most of us, for most mortals, I would say, chess, is normally a system two activity, So you have to think a lot about what you're going to do. Part maybe, is unconscious, part is conscious. But at the same time, if you play chess, or you many matches of chess, you become an expert and so on. A lot of what goes in chess playing becomes automatic, and you have to think only a bit. So by putting learners and solvers in this way, so this is not to say that you cannot do learners play chess, because of course I mentioned that is one of the greatest achievements, the systems that how to play chess and how to play Go, even learning just by self-play alone. What I'm trying to say is that basically with enough experience, many things that normally will belong to the system 2 sphere, can pass to the system 1 sphere. So System 1 and 2 in the human mind, these are two processes, but they are not thought to be independent. System 1 is thought to be evolutionary older, and System 2 in some sense is sitting on top of this System 1. But the crucial part is that they work together. So we have to delineate some of the challenges, in order to get some general artificial intelligence, of some sort. I will say that some of the challenges have to do with this sort of integration. So we did integrations, that works both ways. So an integration that helps learners and help solvers and to coordinate in order to get and tackle problems. This is not completely new, so the AlphaZero program from DeepMind, that is basically the one that achieved world performance, by self-playing in chess and in Go and so on, is actually an example of this integration. On the one hand, you have a learner, you have a deep reinforcement learning, but this reinforcement learning is using a planet to speed up, and even to make feasible this learning process. In this case, the planner or the solver, is a Monte Carlo tree search solvers. So the question is, can we get integrations of this sort that are general? Do we have them? And once again, let me go back to our blocks world. So AlphaZero can do chess, can do Go, but cannot do blocks. And, so before I start getting mails about deep reinforcement learning approaches doing blocks, let me be clear about a methodological point. Doing blocks is not having a coverage of 68% on selected instance with 7 blocks. By doing blocks, you achieve near 100% coverage on arbitrary instance. That is something important, because of course there are many papers that report results on solving blocks problem, but I would say that the standards will not fit these descriptions. By the way, if you want to do blocks work from images, that's challenging enough, and try to solve as different instances as you can, but be aware that if you solve blocks work problems from the screen, you are not solving arbitrary instances, because in those cases, the goal state is one state, the one that is shown. What normally, the goal is just a set of states. If you want to solve arbitrary instances of blocks work, just to mention one domain among many, many others, but it's something that we are all very familiar. So in some sense, you will even have to move beyond that, because it doesn't fit. So there are some representation bottlenecks, have to be addressed in order to apply to problems as simple as this. So we are not in the singularity yet, at least until we solve blocks world. So some other sort of challenges related to this need of an integration between learners and solvers. So one thing, for instance, of course, model learning, but even something more basic. We want to be able to learn the state variables of a problem from streams of actions and observations. And once again, There is a lot of work about getting some performance and report some numbers, but very little work on trying to get the state variables, something that should be feasible, whether using prior knowledge that is genetic or not. Some other challenges, learning useful generalized features for planning, model learning, and actually something that I will not say much now, it's about learning finite abstract representation, okay, for obtaining general plans. Actually, one way that you could fit in principle problems like blocks, world, and so on is if you manage somehow to get these problems that requires, okay, arbitrary inputs of arbitrary size, okay, to project them on finite abstractions. And these abstractions depend on the goal. So one way to get about this challenge is to get the suitable abstractions automatically, okay? And if interested in this topic, I'm not going to solve this problem, but I'm just going to specify and illustrate how to solve it by hand, okay, in the next KR and planning session that follows this one. Okay, so how much time left do I have? So actually, I think I'm doing pretty well. We're going to have time for questions. Okay, good. Finishing these general talks about AI, okay, one listened a lot about the social impact of AI and technology, so I thought, okay, I'll take the opportunity to share a few thoughts, especially, okay, maybe some thoughts that are not completely in the mainstream, okay? So, first, okay, AI, okay, my view is very far from human-level intelligence. Doesn't mean that in certain islands, okay, you can achieve superhuman intelligence. But of course, the fact that we don't have human-level intelligence doesn't mean that AI can't be used for good or for ill purposes, okay? So you can do a lot of harm or sometimes a lot of benefit as well. So actually, people gather, okay, in AI, and they come up with the Asylum AI principles that basically go about this, okay? How, in some sense, to get the best of AI and how to avoid the worst. These principles are very good and signed. I guess that most of you signed as well, okay? But we should be aware, okay? These principles are very hard to enforce, okay? So it is great to have AI systems aligned with human values, but why stop with AI? Why not align technology in general with human values? Why we don't align politics, okay? Why we don't align economics, okay, with human values? Are they actually aligned, okay? So there are reasons to think that they are not, and that there are many forces at play, okay, that have to do with these developments, okay? In particular, I will say markets and politics that are increasingly focused on the bottom line, okay? Profits, getting elected, any cost, okay? And that they normally target our system one, okay? However, we live in a modern society where reasons, respect for the facts, and in some sense the guidance of the common good is what is actually needed, okay? But in some sense, that doesn't mean that they don't come automatically. So to conclude, okay, what I will say that if we want good AI, ethical commitments, ethical committees are good, but what we actually need is to struggle for a good and decent society. Okay, thank you. I try to be controversial, okay? So
Hello. Right here.
Okay.
My question is about learners. You mentioned that deep learning, reinforcement learning are performing quite well in specific tasks, and they have become popular thanks to the compute power available for us now. Given that we know the compute is going to increase for the next decade, can we not just assume that these methods will become better, the surface area solved by them will be larger?
Mm-hmm. Okay, thanks. Actually, I would say that more data, CPU power, and everything, okay, are essential ingredients to what happened in deep learning and so on. But of course, the ideas, okay, so the ideas and the techniques were very good, and okay, it took some time, okay, to show how good they were, okay, at least practically. Okay, my point about, so I know many people criticize or are not too happy about the amount of data, the amount of CPU power, and so on. I tend to think that my point is a bit crisper, okay, about deep learners and deep reinforcement learner, is that basically you cannot solve new problems from scratch, okay? You need to accumulate experience, okay? So now, if you can accumulate experience very quickly on anything, yes, in some sense, why you will need something like a system to inference. I don't think that we are any close to that. And basically, one of the many problems, okay, that arise when you're trying to have self-driving car in the streets is because you cannot trust these system one black boxes, okay? In some sense, you need some understanding of what's going on, else it's very hard to trust. So, so I think that there's going to be a limitation. It's not going to be fixed, okay, probably by CPU power alone.
So, hi. Thank you for a great talk. As a cognitive scientist, I really appreciate the focus on knowledge and representations and so on. I just wanted to get your thoughts on this kind of interplay between System 1 and System 2 and how we might be able to implement that in AI. Because as you said, for humans, we recognize when we have to take over control from System 1. We recognize that an elk has just walked out on the road. We need to get acting and thinking very hardly, and we can't continue talking. How do you see that implementation, sort of?
Okay, thank you. Yeah, that's basically the type of challenges. So I think it's a challenge. There is very little integration, okay, from the top and from the bottom. I think that we are at a time that the bottom-up approach, let's say the learning approach, has been doing extremely well. And so researchers are still sort of trying to apply this method to more complicated problems, okay, not trying to, in some sense, fill this gap or feeling the need to fill this gap. I would say that more generally, that there is a couple of methodological approaches that one can take from any technique, not just deep learning or deep reinforcement learning, is try to see how far you can push this method. What are the most complicated problems that you can solve or deal with, and so on. Or, at the same time, there is another approach, is what are the simplest problems where these methods fail. Okay, I have to say that I have a slight preference for this other method, and that's why I mentioned something concrete as Bloch's wall, because it's very simple, but in principle there's no way that you can tackle that now. But I think that's a challenge. I would say it's not implementation. It will require ideas and formulations and many other things. Thank you.
Thank you very much.
Hector, on the other side.
Okay, sorry.
Thanks for the great talk. I was wondering, I wanted to hear your thoughts about the challenges of learning models and also the challenges of having these planners that work with the imperfect models, because at least in my understanding, a lot of the mismatch that we have seen now when we talk about reinforcement learning, there's this whole thing about model-based reinforcement learning, but it's very hard to do because we have imperfect models and we don't know how to compose predictions and things like that. So I was wondering, what are your thoughts on like integrating those things, and if it's just a matter of we do need to learn better models, or if we need better planners that deal with this uncertainty, and how would that be?
I think we need all of the above, and probably also need more ideas about what needs to be learned. When you see some of the planning algorithms, okay, some of the planning algorithms don't use the model, just some features, okay? So if you get some features right, so you don't need to be accurate descriptions of the state, only these features. So in principle, so I would say that you need everything, okay, to be able to plan within accurate models, but possibly we need more ideas, okay, in order about what to learn. So this is what I mentioned, learning the state variables. So to me, it's not just learning predictive models, okay? So I think that, yeah, we'll see. So, but it's still missing from the picture. Thank you.
Okay. Hector, thank you very much for that talk. It seems to me one of the key issues really is how do we express what we want the computer to do, right? And if we can give a crisp goal statement, then we can give, and if we can write down our constraints relatively compactly, then we can use a solver. But a lot of the successes in deep learning have come in domains like computer vision and speech recognition, where the goal statement, well, I don't know what it would be. It's very, very long, right? The only way we know of to express it is labeling data. And so it's partly because I guess we only solve those problems with system 1. There is no system 2 statement. And so machine learning has been learning directly to system 1 without going through the interpretive stage. So what are the limits of the system 2 to system 1 story? Does it cover a lot, or is it really just a tiny part of all of AI?
Okay, so I agree completely about what you said. So, Tom, that basically there is a lot, in some sense, what solvers cannot get in. Okay, so in a sense, you can think about gradient descent, minimizing error, as being a solver itself that's being applied to that particular task. But I agree that in some sense, the fact that you have these two rival views to tackle problems, it doesn't extend to all problems. It does extend to some. So I would say that right now, some of the problems considered by people in deep reinforcement learning can, in principle, be tackled with very completely different techniques. And I mentioned in particular the point of encounter, for instance, this idea of generalized planning. Because in that case, you're trying to get plans that will work for many problems, that in some sense that's what you want to do with learning. So in that particular area, I can see how these two views in some sense can eventually compete and see, okay, which are the ideas that prevail and why. In the case of image recognition and sound, there is no competition, okay? It's system-wide all the way down, apparently, okay? And
Thank you.
So, Hector, over here, to
Yes.
your left.
Oh, sorry.
Yeah, we're switching
Okay,
one by
okay.
one, just to confuse you a little bit more.
Thank you. Alessio.
Alessio, yes, Imperial College. Yes, I also very much like your distinction between learners and solvers. And looking at AI research right now, it seems to me in the mains, you know, the learners are associated with probabilistic techniques, and the solvers, typically the way we build them, are provably correct. So I wonder whether you agree with this, and whether perhaps we need a little bit more research on correct learners, or probably correct learners, and on the other hand, probabilistic solvers, so to speak, trying to bridge the chasm that actually exists between the two disciplines.
I agree that the main successes, okay, on both sides, as you say, in deep reinforcement learning, have been probabilistic systems for the most part, and in the case of planning, so the best results in some sense are for deterministic systems. At the same time, there are many solvers that are probabilistic, and some learners are used. Yeah, I will say that I would not say that this division has to stay. There is no reason for this to stay. Actually, in the literature about system 1 and system 2, some people I've read that some people that say that system 1 is very bad with uncertainty and system 2 is good with uncertainty. To me, it's actually the other way around. So we are very good about dealing with compiled uncertainty, but we are very bad about deliberating with uncertainty. So probably the uncertainty that we need to go around every day, it's a bit overrated. Okay, I will say, and sometimes using probabilistic models may be too much. Actually, happen even in probabilistic competitions. So it's very hard to have problems where replanners will not do very well. So that's, I would say, another issue. But I completely agree that these two versions, okay, should appear on both sides of this divide.
Thank you.
Mm-hmm.
I would like to add one more aspect and consideration. Which is, even if we had incredible computational power and could process lots of data, there are scenarios and situations we want to reason about as humans, and we want machines to reason about, we will never have data about, and we do not want to create data about. We do not want to create data about major hazards in nuclear power plants and so on, and yet be able to have systems that reason about these situations. How does that fit into your picture?
Yeah, actually, so for instance, we listened today to the talk about moral machines. It's all very interesting, but of course, it's a bit shocking in some sense. We don't think that morality is subject to a majority rule, right? So, and there are many things that we're very comfortable that we do when you are not thinking, that once that you think about them, okay, it's a problem. Maybe it's related to your point. Actually, I'll tell a joke about a caterpillar. I was walking around and easily, and somebody asked, how do you do to coordinate the motion of all these legs? And the caterpillar started thinking, and it couldn't move. Okay, so in a way, when you see about these dilemmas, moral dilemmas that appear in AI, you have to do with this fact that we are thinking about things that so far we haven't thought so much, and we did probably pretty well, and we feel uncomfortable having to talk about whether killing a child or homeless or something. Okay, but thank you. It's a relevant point. Thank you.